is by Cesar Uribe. He's an EC department student at UIUC here in CSL. And the title for his talk is Fast Rates and Network Independence in Distributed Learning.
Okay, thank you. And of course, Adobe crashes. It's back again. They get those minutes back, like a couple of minutes more. Okay. Yeah. So good morning. Thanks for organizing this session. So in this talk, we're gonna go into a little bit more abstract things. It's very nice, these very cool applications of autonomous cars and smart meters and all that. So we're gonna take it down a notch a little bit. So bear with me. So I'm going to talk about fast rates and network independence in distributed learning, and hopefully by the end of the talk you will learn what those terms mean, right? So I'm going to use this, yeah. So this is a collaboration with my advisors, Alex Olszewski and Angelia Nerish. Okay. So what I mean by a distributed system, right? Given the two previous presentations, you can consider this as a network of autonomous cars, right? Like each node is a car driving in the city, and somehow they have some communications between them. And you have these black dot cars, which are the Google cars, and you have the green square cars, which are all the companies, and they are somehow talking to each other because they want to overall provide a better experience for the user. Or you can consider these nodes as smart meters in a neighborhood, and they are talking to each other because they want to detect who's stealing the energy, right? So I'm going to consider a distributed system as a network of processes, right? Doesn't matter right now which processes are we talking about. Can be cars, can be smart meters, can be planes, can be drones, you name it, right? And then let's formalize a little bit what a distributed system is. Right? So we have a network of n agents. Again, cars, drones, smart meters, doesn't matter. And each agent is observing some random variable. Right? This random variable can be, for example, the energy consumption of each node, or can be the traffic at that specific instance in certain roads. Let's say we're engineers like trying to be mathematicians, so we can model this as a random variable. And previous talks talk about how this is very stochastic, so random variables are nice models. And then each node has a set of hypotheses about what is going on with this random variable. And the main problem is that we don't know the distribution of this random variable. We don't know how the attackers will have a probability distributions of doing an attack, or we don't know the exact probability distributions of a traffic jam. Right? But what we have is a model, right? We somehow know if an attack is happening, we sort of, okay, the probability distribution of this attack should look like this, or if a traffic jam is happening, the distribution looks like that. So each node on its own has models about hypotheses of what's going on. Right? You can consider this theta as hypothesis being, okay, there is a traffic jam or not, or there is attack happening or not, and we somehow have models about how these things look like. And then we can construct a set of probability distributions on these hypotheses that we call beliefs, right? What do we believe? Do we believe an attack is happening or not? Or do we believe some traffic stuff is happening or not? right? And just for the rest of the top, I'm going to call these beliefs as mu, right? Which is how likely an agent I thinks and a hypothesis theta is happening at time k, right? How likely this smart meter or at this house thinks there is a thief of energy at this time instant, right? This is great. Like I don't have cool applications, but it matches perfectly. Okay, so, and then how do we model the interaction between the agents, right? So we have a couple of agents and they're connected over a network. And how we model a network is a graph, right? As we have the nodes and we have certain edges that may be changing with time, specifically with the autonomous drivers, right? I don't always have the same car next to me. And then, okay, the graph is this construction of the nodes and the edges, and the edges are changing with time. And also you have certain information on how much do you care about the information coming from your neighbor, right? It's a weight, right? You're getting some information from your neighbor, but you might not care at all what they mean. So, or you may care a lot what they mean. So you have some weights. This is the A term. So how agent I weights the information coming from agent J. And if agent J can send information to I, that means that there is an edge in that network. We were going to consider A, K as nice enough matrices. That means that these are like stochastic matrices, upper bounded. If you see it as a Markov chain, then all the nice things that we care, right? And the graph G is sufficiently connected. Right? In order to a distributed to make sense, you have to have some connectivity, right? If you don't have connectivity in a distributed sense, you don't have a distributed system, you just have a couple of nodes. Right? And what we're going to study specifically is how the network structure affects different convergence results for these type of systems. So let's define what are we looking for in here. So remember, we have certain stochastics process happening for which we don't know their distribution. In this case, is this F, right? Yeah. So this is an unknown probability distributions, but we have a set of models of what might be happening. And we want to find which hypothesis, which of our models matches the closest, or is the closest to the actual thing. Right? Remember, F is unknown. These LIs are what is our models. So we want to solve this optimization problem, which is find the theta in this set that is the closest to what the true distributions of the observations. And one way to measure is, for example, the KL divergence. Right? So we want to solve this joint optimization problem. We want to minimize the overall confidence of a hypothesis about the hypothesis about the true distributions. And we were going to call this consistency, right? If we're able to find the hypothesis that best describes the observations, we're going to say that this system is consistent. And we're going to define this as this limit, right? We want the beliefs on the hypotheses that are not the closest ones to go to zero. Right. So a nice geometric interpretation of this is, okay, we have this triangle, which is the probability simplex, and there is a point here which is unknown, which is the true distributions of the observations. And we have models, right? We say, okay, this distribution can be this, theta 1, or can be this, theta n, or can be this, right? And it's very clear that we have some point which is the closest to the true distribution, which we call theta star. So theta star in this case is the model that we have that best matches the true distribution of the observations, right? So let's say F is attack happening, and this theta 1 is not an attack, this is a failure, and this is an attack, our model of an attack, which is not necessarily the true distribution of an attack, but we say, okay, this is the closest one. So, and what we want is construct a set of beliefs or an algorithm that tells us that, in fact, this theta star is what is happening. So this is my approach, my attempt to make an application, but this is, of course, a toy example. So imagine we have like this grid, and we have 3 nodes. This is like a space, right? X position, Y position. We have 3 nodes, and we're trying to identify the source. But each of these nodes only has distance sensors. So individually, they're not able to identify the location, so they need to cooperate. Right? So what's happening? So let's focus on this node 2. So node 2 observes or measures the distance to the source. And okay, of course, assuming noise and all of these things, then we can say, for example, the observations of node 2, the true observations, are modeled by this black line. And then we can consider what happens if we assume the source is at theta 3, then we have these other probability distributions, and if our hypothesis is theta 5, that means the source is here, we have this other probability distribution. Right? So in this case, it will be clear that the hypothesis that best matches the observations is theta 3. But individually, it's not possible to identify the X and Y position. That's why we need to cooperate. So throughout this talk, we're focusing on the case where individual agents do not have the capability to detect these larger network size events. So that's why we need to cooperate. So of course, this is what I said before. Imagine you have only one agent. The only thing we can say about the position of a source is, okay, this is within this radius, right? Because we only have distance sensors. So what we have is, okay, let's put a couple of more nodes, and let's try to construct this type of probability distributions of where the source might be located. And in this case, these gray shades are plots of the probability distributions of, the beliefs of where the source might be located. So the darker shades means that it's more likely for the source to be in certain position. So that's why we need more sensors, because we want to aggregate these joint capabilities. So one thing that I repeat is not necessarily that one of our models matches perfectly the true distributions of the world, right? Because in general, this is very hard to, every model, what they say, that every model you have is wrong by default, right? It's just how well you can make it. And also, we're allowing for conflicts. That means that it's not necessarily that the optimal hypothesis to be in the intersects of individual optimality. That means that for some agents, some hypothesis might be the best. For some other agents, the other hypothesis might be the best. But what we want is the hypothesis that best matches the whole network of distributions. And what we want this precisely because we might have corrupted measurements, adversarial nodes, faulty sensors, and all that, right? So, okay, you're given a problem. Somebody says you have a prior and you have an observation. The first thing comes to your mind is, okay, let's do bias, right? So this is bias rule. Let's say this is, again, one single agent, imagine. So you have your prior at time k, you have some observation, your model, your likelihood model, and then you construct your posterior. And one interesting thing about bias is that you can express bias as an optimization problem, right? This is the variational representation of bias. And it took us a long time, a couple of months, to figure out that this optimization model is precisely some stochastic gradient descent with some specific functions. So this is very interesting. We could say bias was the first one to invent like gradient descent type of algorithm. But basically, you can prove that what bias does is gradient descent on this specific shape of functions. So now that we have identified how to, for a single agent, which optimization problem is bias solving, we can just propose a distributed version, right? So in the centralized version, what's happening here is that we want to find a probability distribution that is closest to my prior, but takes into account our measurements, right? But now that we are in a network, what we want is we want to find a probability distribution that is on average closest to the price of my neighbors and myself, and take into account my observation. Right? So this is very natural extension, and this is called distributed stochastic mirror descent, right? If you go from the centralized to the decentralized version, which often includes some type of weighting with your neighbors. And when you solve this optimization problem, you get this solution, right? It's very nice that it has a closed form. But what's happening here is that we can prove that the decentralized version of bias is like if you construct a geometric average of the beliefs of your neighbors and then apply bias. These type of algorithms are called non-Bayesian methods because it's not exactly biased, because if that was biased, then your observation, your neighbor's beliefs should be in the likelihood model, but in this case, they're called non-Bayesian or bias-like, which is geometric average of your priors and then likelihood models. So we're going to consider 3 different problems. What happens when your graphs are undirected, what happens when your graphs are directed, and what happens when you have static graphs. And we show we can construct the specific algorithms for these 3 cases and prove explicit geometric network independent rates of convergence for these algorithms. So this is our main contribution, right? So in the case of undirected graphs, we can just apply the bias rule that we have, right? So bias with geometric average of your neighbor beliefs as prior. This is what's happening here. Geometric average and then bias. This is the first algorithm for undirected graphs. When the graphs are directed, then things complicate, and you need to use other type of machinery, specifically, for example, push-sum type of algorithms. So we have constructed these, taking ideas from push-sum, like we can construct this algorithm where you have, again, a geometric average of your priors, but some specific version of your weights, and this extra random variable. I mean, if you go into literature on push-sum algorithm, you can easily see how this translates into the original algorithm, but this is a way to handle directed graphs. And finally, in static graphs, we can have some acceleration, right? So we can construct this other type of algorithms for when the graphs are static, and that looks this nasty relation, but the main key point is that you have geometric average of time k and geometric average of time k minus 1. So you have like one-step memory type of things. So the general form of the theorems I'm going to show is the following, right? Under appropriate assumptions, a group of agents following algorithm X, which is any of the 3 algorithms that I showed you before. There is a time that depends on the number of agents on the graph and on this parameter rho, such that with probability 1 minus rho, after this time, then the beliefs on the hypotheses that are not optimal decays exponentially, right? So it's something like this. You have to wait this time n, and after this time n, your beliefs decays exponentially. So you're going to converge exponentially fast. But what we care now is how these 2 constants, C2 and C1, changes with the number of agents. So these are my specific results. So for the first algorithm, the time you have to wait is inversely proportional to this rho. Remember, this happens with probability 1 minus rho. So the more certain you want to be, you have to wait more time. C2 is constant, and C1 can be n cubed log n for the worst case graphs, or if you have nice weights like lazy metropolis, then you get n squared log n. For the time varying directed case, remember the push-sum version, sadly we found that the push-sum algorithm is exponential in n, so there is no polynomial time for this type of graphs. So again, we have to wait at time n, C2 is constant, and C1 can depend if the graphs are regular, we have n cubed, but if we have any directed graph, we have n to the power of n, which is very bad, but it's the best we can do so far. We don't have polynomial time, polynomial and n algorithms for solve directed graphs. And this parameter delta can be, again, very exponentially bad, or 1 if we have regular graphs. And if we have static graphs, the time you need to wait is of order of n, C2 is constant, and Cn is like almost linear, right? So the nicest thing you can have is a static graph. We can define the weights, and the algorithm that we propose, it's going to be linear. But remember, in all three cases, C2 is constant, right? C2, C2. So, and look at this graph. So the C2 is the term that is multiplying K specifically. So what's happening is that in all the three cases, the convergence rate after you weight this time is network independent. So we have managed to take the network out of the rate. And what this means, it doesn't matter which type of network do you have. After you wait this certain time that depends on the graph, all your beliefs will converge exponentially fast regardless of the network you put. So the network basically disappears, and it's like if you had a centralized system. So I'm going to finish right now. Okay, this is some graphs that showing that indeed we can find graphs that matches. So this is the number of iterations that you require for three different types of graph for the three algorithms that I show. So again, we have almost linear for static graphs, then linear, n-squared type of things, and then in cube. Yeah, and just to finish, we have considered a set of finite hypotheses, so we're working on extending this to a set of continuous hypotheses. Also work on efficient communications of the beliefs. So as of now, we require communication for probability distribution, so some sampling could be improved there, and also tracking of dynamical processes. And this means going into lands of Kalman type of estimation and getting exact bounds for these distributed systems. And yeah, questions, and you can ask me for the details or look into these papers. The solution, theta star is the solution to the optimization problem. We assume it's not that. Yeah, that's one of our main contributions. Well, if theta star is empty, then there is no optimization problem, right? Yeah. Yeah, but that's precisely what we're doing. Then, let's say for agent 1, the best hypothesis is theta 1. For agent 2, the best is theta 2. But if they talk to each other, the best hypothesis for both of them might be theta 3. Right? You mean?
The definition of theta star.
Wait. Should be around. Yeah, this one, right?
No, the next one. The intersection. Yeah.
Oh, yeah. That is not necessary, right?
Oh, I'm
It's not. Yeah, it's not. Yeah.